Thank you for this opportunity. And okay, I work quantum machine learning, and quantum machine learning is a field at the intersection of mechanics, quantum physics, and machine learning. And it depending on the type of algorithm and the type of the data, it can be divided in these 4 quadrants. So if you use classical machine learning methods on classical data, you have quantum inspired machine learning models. And if you use, you can use the classical machine learning models on quantum data during this quadrant, or you can develop machine learning models using quantum computers. And is it working? Yeah. Is in this part of this quadrant. And you can apply the quantum machine learning models on both on classical tasks or quantum tasks. In this talk, I will talk about works. Okay. Okay. I will talk about two works that are on this quadrant here. So they are we train the classical machine learning models that works on quantum data. So for the first work, we use simulations, and we consider a random walker on a quantum network, on a complex graph, basically, that is perturbed by a noise. And the objective is to discriminate the noise that was used to perturb the dynamic using only the measurements of the populations of the quantum random walker. And we use both support vector machines and neural network and recurrent neural networks to train the models. And well, we found that the parameters of the quantum walker dynamics were crucial to the classification capacity of the models. And if you have a short evolution time with a high sampling frequency, the task is easy. If we have a long evolution time, more delayed in time, the task is hard. Overall, we obtain 90% of accuracy in the classification between 2 Markovian noises, IID, or 2 non-Markovian noises that influence the 2 different quantum dynamics, or 1 IID versus 1 non-Markovian. And overall, the setting was this. First, we fix a number of states where the walker operates, and 2 different noises that perturb the dynamics. Then we create a connection. Well, we randomly initialize connections on the nodes, and we randomly initialize one of the nodes as the initial population for the walker. We run 2 parallel dynamics of the walker, and for each one we sample basically in time different probabilities of the position of the walker inside the graph. And those measurements are well, obviously, if you do those measurements on a real quantum system, the wave function collapses, and you cannot perform these straightforward on a quantum computer. But on the second work, you will see how to apply to a real machine. In this case, we simulate is a simulation, so and thus we we can calculate the probabilities also in the middle of the dynamic. And so those are the probabilities of at time 0, time 1, and so on for the first dynamic. Those are for the second. And we repeat all this part, reinitializing a random graph and evolving the system in perturbed by two noise. And we create a data set of the population probabilities for the labeled with the labels for the two different noises. And we trained machine learning models to predict which one of the noise was used to perturb the dynamic, reading only the population probabilities. Here you can see two examples of the population probabilities for the last 5 of 40 nodes. And in general, we used 15 time steps and 2 different sampling frequency, let's say. So here the dynamic is shorter and here is larger, and here it doesn't have time to how to say to diffuse in all the graph, while here you can see it have more time to diffuse. And to develop the machine learning models, we use the SVM that you probably know, but it works by finding the parameters that of the hyperplane that divide the two classes of data, and there is the kernel trick when the data is not linearly separable. And we use also a neural network that basically are a set of artificial neurons arranged in layers, and each one is a nonlinear function, basically. As a loss for the neural network, use the categorical cross entropy that is commonly used in classification tasks. And well, at the end, we have a softmax because we need a probability distribution. Recurrent neural networks are a neural network specialized in the processing of a sequence of data. And in general, when you have a data that is in the form of a sequence, a temporal or other kind of sequence, can be processed by a recurrent neural network iteratively on each steps, using basically a set of parameters that is shared on all the time steps. And you have a hidden state that is carried through each one of the steps that basically is like a sort of memory. And at the end, you can take the hidden state and you can interpret it like a sort of representation of all the sequence and process it like, for instance, with another multi-layer perceptron. At the end, with another set of parameters that perform the classification. So this is another way of representing a recurrent neural network. And in general, when you have long sequences, recurrent neural networks suffer from the vanishing gradient problems. During the gradient, the calculation of the backpropagation, the first element of the sequence are not do not contribute to the gradients, basically. And there are other models like LSTM and GRU that use gating mechanism to overcome this problem. And RNN can be also arranged in a bidirectional way when you have one network that processes the data in one direction of the temporal sequence, and another parallel network that processes the data in the other direction, from right to left. And they can also be arranged taking different layers of recurrent neural networks. And at the end, you can also not take on, you can, as I said before, take the last value of the hidden as a representation of the network, or do also some sort of aggregation of all the hidden states. In general, this is what I said before. You take only the last element of the last hidden as a representation of the network, the last for the left part and the first for the right part. Or you can do something more, something different, like max pooling. You simply take the maximum between the hidden, or also use attention mechanism that basically are a weighted sum of all the hidden, where the weights are learned along with the network. So in general, as I said before, we have two different data sets with two different sampling frequencies of the measurements. And for each one, we have three different data sets. One where the dynamic is perturbed by two different IID noises. Two different non-Markovian noises. Well, different, but they have the same support. And one with a Markovian and non-Markovian noise. And we train the model that read only the last measurement, like the probabilities, populations of probability at the last time. Or also we train other models that they interpret all the sequence of measurements. For the first, we train SVM and the simple multilayer perceptron. And when for the sequence, we use SVM with the stick probabilities and several different models of recurrent neural networks. And for each one, well, we do every parameters optimization and so on. For the first data set, we found that, well, the task is quite easy for the IID and the versus problem. And we obtain those accuracies, basically. And while for the second task, yes?
Can you please explain one time the columns? What are the meaning of the columns?
These three columns are for the data sets, the data set with a shorter dynamic, basically. So the sampling frequency of the population is higher, and the other three here, the sampling frequency is lower, but we still have 15 sampling, basically. IID means that the quantum dynamics is perturbed by a noise that is sampled from a distribution that changes over time, but the distribution, the changing of the distribution does not depends on the previous sampling, basically. Non-Markovian means that the change of the distribution, and WES means that we use one distribution that is Markovian and one not Markovian. Okay. And well, when the sampling frequency is lower, the task is more difficult, and for the if you read only the last measurement is not enough to train a classifier, basically. Is not learning anything, and also the values are lower for the using all the sequence, and also overall the task of discriminating between two non-Markovian noises is more difficult respect to discriminate two Markovian noises. Okay.
Just to see if I understand the table well. So you said that the sample frequency changes, but the number of steps is the same.
The number of steps is the same, 15 steps.
So the second table, you are far away from the initial state.
Is more far away. Exactly.
So is that the reason why it's more difficult to distinguish?
Can be the reason, yeah. Because it's more diffuse and
so each sample size that you give to the classifier is at a fixed time slice, no?
Sorry, each sample.
So the classifier is distinguishing between the two
The two noises that.
But at each step you inject the sample, two samples which are taken at fixed time. So it's the probabilities at a given t, no? It's not the
it's a probability at a given t. Yeah, exactly.
Okay, so it's a c. So it's each. I see. Okay. Okay. Thanks.
Okay. So this work was with simulated data, and for the second work that I present here, we data collected from real NISC device from IBM. This is the circuit that we use. If you're not familiar with the quantum circuit formalism, basically each one of the lines is a qubit, and each one of those is a unitary operation, is a quantum gate, basically. Those are one qubit gates, an Hadamard gate, not, and those are two qubits gates, C naught, and this is a 3-qubit gate, Toffoli or CC naught. And those are the measurements on only 2 qubit, and those are the bits where you put the measures, basically. So also in this case, we had a temporal dimension. Obviously, we cannot, well, first of all, this part of the circuit is repeated 3 times. And we measure the circuit after each C naught and after each Toffoli gates. And obviously, you cannot put measurements in the middle of a quantum evolution. And to do this, basically, we reinitialize and restart the circuit. We run it until the measurement. We collect the measurement and we restart, reinitialize with another piece of the circuit, and we run and so on. Okay, and we have now nine measurement steps. We collect 2 different data sets. One we call the fast and one we call the slow. Fast means that is a data set of temporally closed executions. Basically, we make as much as execution we can on the IBM machines. We use 7 different machines, and for each device, we collected 2,000 sequences of 9 steps, and each measurement is obtained running 1,000 shots of the circuit. With this fast data set, we did several tasks. The first is the binary classification of which device was used to run the circuit, because well, the circuit is always the same. So theoretically, the measurement should be always the same. But we train the machine models to discriminate which one of the machine was used to perform the circuit. And we consider both a single point of measurement or the incremental measurement. And we trained, in this case, we train SVM classifiers because they were already enough to learn these to learn this task. And also we did hyperparameters optimization with the different kernels. Those are the results for the binary classification. Well, the table is cut, but it's not important. And those are all the machines, the 7 machines, and each box of those is the results of the training of a binary classifier that classify, for instance, in this case, Athens and Bogota. Those are the name of the IBM machines. And for each one, the first column is the step index, K. The second column is the accuracy that I called alpha. reading only the K index. So for instance, the 0.954 is the accuracy of the model trained reading only the measurements at this fourth step. The third column are the accuracy reading all the measurements from the first to the case. So for instance, for the fourth step, we use as input all the measurement at step 1, step 2, step 3, and step 4, and this is the obtained accuracy. From this table, we can see that using only a single measurement is not enough to train a good classifier. Because the second column here is not monotonically increasing, and is for some measurements you have a good accuracy like this, but for others you can also have a bad accuracy. While if we use the several measurements, we always obtain a perfect classifier, basically, using a simple model like SVM. And we trained also a multi-class classifier. Basically, it's a SVM in a 1 versus rest setting. And also in this case, we see that reading only one probability is not good. We have low accuracies. And if we read already 2 consequent probabilities, we have a good results, with 3 even better results, and so on. And also we perform a time classification. That means we run we collect 2 data sets on the same machine, Casablanca, on 2 different days, basically. And also in this case, it's possible to train a classifier that almost perfectly find which one of the machine was used to run the circuit. So, well, basically that means that there is a noise fingerprint both related to the machine, and this noise fingerprint on the measurement is changing over time also. The slow data set is similar to the fast. The difference is that the collection of the data is delayed in time. In practice, we wait at least 2 minutes between each collection of data. And here you can see the plot of the number of runs with the lapses hour, and these strange delays here is because the IBM use a fair share queue policy. If you use a lot of quantum machine, after a while they reduce your priority, and basically they slow you the execution of your tasks. And well, we use 2 different machines, Belém and Quito, and also in this case 2009 steps. And in this case, with this data set, we perform time window classification. Basically, we take one machine, the one that were steadier in time, and discriminate between the first window of 200 runs and the subsequent window in times. And that means, well, the first part, the top part, is they are the accuracies reading only the probabilities at step K. The bottom part is they use the cumulative probabilities from the first to K, and that column is the accuracy obtained classifying the first window from the second window, this column from the first window, the third window, and so on. And well, also in this case, we can see, well, the same as before, the single probability is not enough to train a good classifier. But if we use the collect, well, all the probabilities, we obtain perfect classifier, basically. And here you can see another task where is the accuracy discriminate using all the probabilities, discriminate of all the steps, discriminating the first window from another window that initially is next to the first one, and then is moved over time. And this is the gap between the windows, basically, and this is the reached accuracy. So we can see that after after some few hours is already, you can discriminate which window was where run the code, the circuit. And we perform also a robustness analysis. So in this case, we use both machine of the slow data set, and this is the accuracy obtained training classifier that use all the steps, and we trained on the window in the row index. So for instance, for the first row, we trained the model to discriminate the two different machines only on the first window of 200 measurements, and we test on the window in the column index. So for the diagonal, we test on the same window, and here and outside the diagonal, we test on the other window. And for some cases, as expected, the reached accuracy is decreasing when you with the distance from the diagonal. But we found that after a while, for those cases, we are far in time from the window where we trained the model, but is still working to discriminate which machine was used. For this, this means that the fingerprint that is related to the machine is much stronger respect to the one that is related to time. So the fingerprint is changing over time, but you can still discriminate which machine was used after some time. And well, that's all. Thank you. If you have a question. Thank you for the questions.
Sorry, you measure the robustness?
So
variation with respect to the.
So basically, we have this data set. We split it in windows of 200 runs, and for instance, for the first row, we train on the first window. So we use the data here to train the model, and we test it without retraining the model on the second window, the third window, the fourth window, and so on. And for instance, here is the model that was trained on using this data and test using this data. That is several hours after the data where it was trained. Okay.
Hi, Stefano, thanks for the nice talk. So I just have some trivial doubts about the first part of your talk about noise classification. So what do you mean by when you say that you want to classify, you want to distinguish between two non-Markovian noises? So does this mean that there is a particular noise model and you are trying to do classification between two noise strings, or is it just two different noise models altogether?
So basically, The quantum dynamic, the population probabilities, the worker is perturbed with a noise that is sampled from a certain distribution that changes over at each step of those time steps, basically. Also, the noise distribution is changing, and basically the difference between the two is the support of the noise distribution is always the same, but the difference is the probability distribution on where you sample the noise. Basically, the factor that make you the probability distribution changing, basically.
And also the second question is that did you use any real device for?
No. This is all simulated.
Okay.
The second work was with the real devices.
Okay, thank you very much.
Thank you. Thank you for the very nice talk. But when you try to classify between two different sets of noises, I'm sorry, I'm very ignorant, but the idea is that if you apply this in a real life scenario, you want to be able to distinguish between which two types of noises in the application. This type of family that you're describing, and you trust that this generalized to tell you which noise are you really measuring. That's the idea.
Well, obviously, if you want to apply this to a real setting, you don't have the ground truth for the for the noise distribution. Well, the second part of the talk was how to say, inspired from the work here. So you have two different machines, and obviously you have two different noises, and this is because we did the second part basically. And but here, well, you need to find a way to, or you find a way to have the ground truth, like using some noise spectroscopy method or something to get the ground truth of the noise.
But if you have the training set and then you trust that the same that you can generalize, you don't need the ground truth. You can use it only to classify and trust the performance. No, you don't need to relay. If you could label all the time, you don't need to try to do an algorithm. In the sense that now you have this classifier, you want to apply it to unlabeled data, no? In a sense, yeah. So the idea is that if you apply this type of classifier to unlabeled data, you can tell if it's between the two types of noises that you train, you can tell which one you have. That's the idea.
Yeah, basically you're to train the model with simulated data and apply to real data.
Yeah.
This can be tricky sometimes because well, at least you need to have a way to validate the model on the real data also.
Oh, okay. Yeah. Thanks. Very interesting.
Thank you.
So just another question about this. I didn't quite get if you already. So if you already replied or not, I'm sorry if you already did. So in this case, are you interested to characterize the noise or just to say whether in the two cases the two noises are distinct, are different?
No, in this case, all is classification. So the two kind of noise are different.
You only want to know if noise 2 is equal to noise 1.
Exactly.
You're not interested in characterizing.
Exactly. Yeah. Exactly. Not in this case.
Okay. Thanks.
Okay, so let's then
Okay.
speaker again.
Okay. Thank you.